I wanted to talk about how a t-test can be a left-tailed test, a right-tailed test, or a two-tailed test. A little bit earlier I talked about the difference between a one-tailed test and a two-tailed test. A left-tailed test and a right-tailed test are actually two different types of one-tailed tests. So you can actually have a left-tailed test, a right-tailed test, or a two-tailed test, and I'll talk about what the differences are between these. In a person who's doing a left-tailed test is expecting a data set with a negative t-score. They're expecting the t-score to be negative, and the researcher is also expecting to compare the negative t-score to a negative critical value. So the researcher who's doing a left-tailed test is expecting to get a combination of participants that will have a t-score at the left end of the curve, or at the negative end of the curve. The t-score at the center is 0. So the researcher is expecting to get an outcome somewhere down here at the negative end, and they're going to compare it to this negative critical value. The critical value is a negative number because it's at the left end below 0. And this negative critical value that they're going to be using is actually the value that has 5% of the curve to the left of it, meaning 5% of the possible combinations are below this critical value that's used in a left-tailed test. And what the researcher wants to do is to get an outcome somewhere in this area that's to the left of the critical value. They want to get an outcome somewhere in here. And this area at the left end, right here, below the critical value is, or to the left of the critical value, is called the rejection region. So the rejection region of a left-tailed test is at the left end of the curve. It's this 5% piece right here. And in a left-tailed test, a researcher isn't planning to use a positive critical value because they're expecting to get a negative t-score, and a negative t-score has to be compared to a negative critical value. In a right-tailed test, a researcher is, did I say the researcher? Maybe I should say a researcher who is planning to do a right-tailed test is expecting to collect a data set with a positive t-score, and is expecting to compare a positive t-score to a positive critical value. which means a person who's doing a right-tailed test is expecting to get a t-score somewhere at the positive end. They're expecting to get one of these combinations at the right end that will give them a positive t-score, and they're planning to compare that positive t-score to a positive critical value. If you get a positive t-score, you have to compare it to a positive critical value. Just like how if you get a negative t-score, you have to compare it to the negative critical value. And the positive critical value in a right-tailed test is actually the critical value that has 5% of the possible combinations to the right of it. 5% of the combinations have higher t-scores than this critical value. Because this number line is showing t-scores. And in a right-tailed test, the rejection region is at the right end of the curve. It's in this area here above the critical value. So the researcher wants to get a data set in this area in a right-tailed test, because an outcome in this area will let the researcher reject the null hypothesis. The researcher wants to get an outcome above or to the right of this positive critical value in a right-tailed test. Now someone might ask, what if a person is planning to do a left-tailed test and they end up getting a positive critical value that they didn't expect? No, wait. Someone might ask, what if a person is doing a left-tailed test and they're expecting to get a t-score at the negative end, and they're expecting to compare that t-score to this negative critical value, and the researcher actually ends up getting a positive t-score that they didn't expect? What does the researcher do then? Well, if the researcher ends up getting a positive t-score, the researcher can't do the left-tailed test that they were expecting to do, and they have to change their plans, because in order to do a left-tailed test, the person has to get the negative t-score that they were expecting. Just like how if a person is planning to do a right-tailed test, and they unexpectedly get a negative t-score down here, person can't do the right-tailed test that they were planning to do, because in order to do a right-tailed test, you have to get that positive t-score that can be compared to the positive critical value. If you end up getting a negative t-score down here, you can't compare it to this critical value up here that's at the positive end. There's also a two-tailed test. A researcher who is planning to do a two-tailed test does not have a specific prediction about whether they will get a positive or negative t-score. The researcher is simply planning to compare the t-score to a negative critical value if the t-score turns out negative, and is planning to compare the t-score to a positive critical value if the t-score turns out positive. So a person who's doing a two-tailed test doesn't feel confident, or doesn't feel very sure about whether they're going to get a negative or a positive t-score. So what that person doing a two-tailed test is going to do is just that person's going to wait to see if they end up getting a positive or a negative t-score. If the t-score comes out to a negative number, they'll compare it to the negative critical value down here. If the t-score comes out to a positive number, they'll compare it to the positive critical value up here. And this researcher who's doing a two-tailed test has two rejection regions. If they end up in this area, if they end up getting an outcome in this area to the left of the negative critical value, which means that they get an outcome with a t-score that's further to the left of this critical value, they end up in the left rejection region. If they get an outcome with a t-score that's above the positive critical value, they end up in this positive rejection region. So the researcher just waits to see if they get a positive or negative t-score. If the t-score turns out negative, they check to see if they're beyond the negative critical value in this rejection region. If the t-score turns out positive, they check to see if they're beyond this critical value in the positive rejection region. So the researcher is basically hoping to get an outcome in either rejection region in a two-tailed test, because an outcome in either rejection region will let the researcher reject their null hypothesis. And what actually happens in a two-tailed test is the entire rejection region, which used to be 5% at one end, actually gets split in half, where 2.5% of the possible samples or combinations are beyond this critical value down here, and only 2.5% of the possible combinations or samples are in this rejection region. The reason is because you don't want the total size of your rejection region to be too big. You typically don't want more than 5% of your curve area to be a rejection region. So in order for the total rejection area to stay 5%, it has to be split in half at the two ends. If both rejection regions were 5%, then 10% of the total area would be a rejection region, and it would be too easy to reject the null hypothesis. So in order to keep it from being too easy to reject, you have to make your two rejection regions smaller. They can only be half the size as this rejection region that's used in a right-tailed test or a left-tailed test. And the total rejection area is actually comes from the level of significance. If you're setting your level of significance to 0.05, like I said how it's usually set to 0.05, then that means that your total rejection area will be 5%, which it is in all three of these curves. And so what else is there? This covers the rejection regions in these three types of tests. Also, in a one sample t-test, the alternative hypothesis depends on what type of test you're doing. In a one sample t-test, a researcher who's doing a left-tailed test has a reason to believe that the population mean is below the number being tested, and is also predicting that the mean of their sample will be below the value being tested. If a researcher is testing whether the average age of a Cal State student is 23, and the researcher has some reason to believe that the population mean is under 23, or under what's the number being tested, then the researcher would do a left-tailed test. And if the researcher is predicting, if the researcher has a reason to believe that the population mean is below 23, they would also expect their sample mean to be below 23, because if the population mean is below 23, your sample mean should follow that, and it should also be below 23, because the sample comes from the population. A researcher who's doing a right-tailed test has a reason to believe that the population mean is above the value being tested, and is predicting that the sample mean will be above the population mean being tested. So a researcher who is testing whether the mean is 23 and has a reason to believe that it's actually above 23 and is predicting that their sample mean will be above 23 is doing a right-tailed test. And the alternative, the null hypothesis in a one sample t-test simply shows that the population mean equals the number being tested. That's what it says in all three tests. But the alternative hypothesis is actually what the researcher is hoping to show evidence for. And that's actually different in the three types of tests. The null hypothesis is just what the researcher is trying to show evidence against, it's what the researcher is trying to reject. In all three types of tests, the researcher is trying to reject the idea or the possibility that the mean simply equals the number being tested. So they're all of the null hypotheses are the same. The alternative hypothesis, which is down here, HO is null, HA is alternative. Sorry if I didn't say that earlier. In a left-tailed test, the researcher has a reason to believe that the population mean is below the value being tested, which means the researcher is actually hoping to show evidence to support their belief. They're hoping to show evidence that it's below the value being tested. So what the researcher is hoping to show is that it's below the value being tested, which is why there's this less than sign. This is the number being tested in this blank right here. So the alternative hypothesis is what the researcher is hoping to support. So in this case, in a left-tailed test, the researcher is hoping to support the possibility that the mean is below the value being tested. In a right-tailed test, the researcher is still trying to reject the possibility that the mean simply equals the value being tested, which would go in this blank right here. But the alternative hypothesis, which is what the researcher is hoping to support or show evidence for, is actually the possibility that the mean is above the value being tested, because the researcher believes that the population mean is above the value being tested, and the researcher is trying to support their belief. So the belief that the researcher is trying to support is what's shown in the alternative. The researcher is trying to support their belief that the mean is above the value being tested, which is why you have this greater than sign. In a two-tailed test, the researcher is still trying to reject the possibility that the population mean simply equals the value being tested. But now the researcher doesn't have a reason to believe ahead of time whether the population mean is above or below the value being tested. The researcher is basically just hoping to reject the possibility that it's equal to the number being tested, and to support the idea that it simply doesn't equal the value being tested. So in a two-tailed test, the researcher is simply trying to support this possibility that the mean simply doesn't equal the value being tested. And they're not trying to support a specific direction. They're not trying to support that it's below the value being tested, or trying to support that it's above the value being tested. They're just trying to support the idea that it simply doesn't equal that number. So I In all of these, HO, or the null, is what they're hoping to reject. And HA, or the alternative, is what they're trying to support. One way to remember these is to remember that in a left-tailed test, the direction sign points to the left. In a right-tailed test, the sign points to the right. In a two-tailed test, it just has this not equal sign. So in all three types of tests, this is what they're hoping to reject, this is what they're hoping to support. And what they're hoping to support is different across the three types of t-tests. Let's also look at the independent samples t-test. In a left-tailed test, the researcher has a reason to believe that the population mean is lower than has a reason to believe ahead of time before the study that the mean of population 1 is lower than the mean of population 2. And the researcher is hoping to support this belief that they have, which means in a left-tailed test, they're trying to support their belief right here that the population mean, the mean of the first population, is lower than the mean of the second population. And they're hoping to reject this possibility that that the two means are simply equal. So this is what they're hoping to support. In a right-tailed test, the researcher has a reason to believe ahead of time before the study that the mean of population 1 is higher than the mean of population 2. And the researcher is hoping to support that belief. So the belief that the researcher is hoping to support, or the possibility that the researcher is hoping to support, is right here in the alternative. They're hoping to support their belief that the mean of population 1 is higher than the mean of population 2. And they're still trying to reject this possibility that they're simply equal. In a two-tailed test, the researcher doesn't have a specific belief ahead of time or about about which population mean should be higher than the other one. The researcher simply wants to support the possibility that the two means aren't equal, that they're different in some way. So in a two-tailed test, they're hoping to support this alternative hypothesis. And they're still trying to reject the idea that the population means are equal, so that's still the null hypothesis. And in an independent samples t-test, in a left-tailed test, the direction sign points to the left. In a right-tailed test, it points to the right. And in a two-tailed test, it's simply a not equal sign, just like in the one-sample t-test. The last one is a paired samples t-test. In a paired samples t-test, in a left-tailed test, the researcher has a reason to expect or to believe that the mean of population 1 is lower at time 1 than at time 2. Remember, a paired samples t-test is comparing or looking at whether the mean of a population is higher at one point in time than at another point in time. In a left-tailed test, a researcher has a reason to believe that the mean of that population is lower at time 1 than at time 2. So they're trying to support this possibility. What mu-d stands for is the mean. Each member of the population has a different score that can be calculated by subtracting the score at time 1 by the score at time 2. So the entire population has a different score that shows the amount of change from time 1 to time 2. And if all of those different scores across the population are averaged, you get a mean difference score for the entire population. If the mean of population 1 is lower at time 1 than at time 2, it means that the mean difference score of the population is less than 0, which means a negative change. Well, if the mean of population 1, if the mean of the population is lower at time 1 than at time 2, meaning the mean of the population is 30 at time 1, and the mean of that same population goes up to 40 at time 2, which means the population mean is risen or gone up. It means that the difference between time 1 and time 2 is below 0. If you subtract the mean at time 1 by the mean at time 2, you get the mean of the difference scores. So the mean of the difference scores for the population is a negative number when the mean is lower at time 1 than at time 2. So this is what the researcher is trying to support in this left-tailed test. They're trying to support the possibility that the mean of the population is lower at time 1 than at time 2, and that the mean difference score of the population comes out to a negative number, or less than 0. A right-tailed test is the opposite. When a researcher has reason to believe that the mean of the population is higher at time 1 than time 2, then this is what the researcher is hoping to support. They're hoping to support their belief that the mean has gone up from time 1 to time 2. If the mean has gone up from time 1 to time 2, I didn't say that right. A right-tailed test is used when a researcher believes that the mean of the population is higher at time 1 than at time 2. If it's higher at time 1 than at time 2, like this, it means the population mean has dropped from time 1 to time 2. Maybe it's dropped from 40 down to 30. If the population mean has dropped from 40 down to 30, if it's dropped from a higher to a lower number, that means that the difference score will come out to a positive number. If you subtract the mean at time 1 by the mean at time 2, you get the mean difference score. So if the researcher is basically trying to support the possibility that the mean difference score is a positive number, because they're basically trying to support the idea that the mean is higher at time 1 than at time 2. So this is the alternative in the right-tailed test. In a two-tailed test, the researcher doesn't have a specific belief about whether the population has a higher mean at time 1 or at time 2. They're just trying to reject the idea that there hasn't been any change. So what this alternative is saying is that the mean difference score right here is simply not 0. It's either a positive number or a negative number, but not 0. And this is what the researcher is trying to support in the two-tailed test. They're simply trying to support the idea that the mean has either gone up from time 1 to time 2 or gone down from time 1 to time 2. and they're simply trying to support the idea that there's been some change in either direction. And the researcher is hoping to reject this idea that there's been no change from time 1 to time 2, because this, when it's equal to 0, that means no change. So in all three types of paired t-tests, the null says that there's been no change on average from time 1 to time 2. It's saying that the mean hasn't changed from time 1 to time 2. And in all three cases, the researcher is hoping to reject this possibility, which is the null hypothesis. And but the specific possibility that they're hoping to support is different across these types of tests. This is all I have for this topic. If you have any questions about what I've talked about, feel free to ask me.